Hello and welcome to a new physics lesson. Today we'll continue our discussion of electromagnetic induction. Okay, this is chapter 11. Okay, and we'll start by looking at the electromotive force induced in a moving rod. Electromotive force, EMF in short, induced in a moving rod. And we have a formula, E equals BLV, that we want to prove. This formula also shows up in the booklet right here. Okay, so what is this about? Well, we have two rails, okay? This is one rail, this is the second rail. Okay, to remember the word, think about railroad, yeah, which looks like this. Okay, and at one end they are connected. Okay, and they are made of metal. And on top of them, I have a metal rod. Okay. And this metal rod is moving with velocity v, a speed v, which means that after some time, it will show up here. Okay. And by its motion in a magnetic field, an EMF, an induced voltage, will show up. Okay, so another word for EMF is okay, induced voltage. Okay, induced voltage. Okay, and of course, we need to show that we have a magnetic field. And the magnetic field can point down or up. Let's say the magnetic field is pointing up, perpendicular to the plane of the rail. Okay, so the magnetic field B is perpendicular to the plane of the rails. To simplify the calculation, so we don't have to worry about the cosine of the angle. Okay. It's a good time to remember the definition of magnetic flux. The magnetic flux, it is the magnitude of the magnetic field times the surface area times the cosine of the angle. What angle? The angle between the magnetic field and the normal to the surface. So theta is the angle between the magnetic field and the normal to the surface. Okay, so in this case, the normal to the surface is parallel to the magnetic field because both are perpendicular, yeah? Which means this angle theta is 0. It's the angle between two parallel lines, yeah? And the cosine of 0 is 1, so we don't have to worry about it. Cosine of 0 degrees is 1. Which reminds me of a joke. What do you answer if your girlfriend asks you this question? What is my inverse cosine? What do you answer? Well, you have to say 0 because you are the one Okay. Well, anytime the magnetic flux changes, we have an induced EMF, okay? And Faraday gave us this equation. The induced EMF is negative delta magnetic flux over delta time. So the change in time over the change in magnetic flux over the change in time, okay? And this minus in front is there only to remind us of the Lenz's law, yeah? This being a voltage, it can be positive or negative depending on how we measure it, yeah? The sign, okay, that is plus or minus of voltage depends on how we hook up the voltmeter, yeah? So whether a voltage is positive or negative depends on how we measure it. And this minus has nothing to do with the actual sign that you see on the voltmeter. If you swap the leads, the voltage becomes negative, yeah? So if I have a voltmeter here, right, and a 9-volt battery with the plus here and the minus here, if I hook up the red voltmeter wire to the battery and the black voltmeter wire to the minus of the battery, yeah? So this, you'll see COM on the voltmeter, common ground. And here you'll see voltage, okay, voltage, you measure volts. What will the voltmeter tell you? It will tell you 9.00, yeah? But if you have the voltmeter and you hook up the black wire to the plus of the battery and the red wire to the minus of the battery, yeah? That means you stop the connections. What will the voltmeter indicate? It will indicate negative 9.00. Okay? That's something you need to understand. Because the voltmeter will basically show you the electric potential difference, okay, which is So voltmeter reading is, okay, the electric potential at the positive probe minus the electric potential at the common ground, at the black probe, yeah? And for a battery, okay, for a battery, for a 9-volt battery, the electric potential at the plus side minus the electric potential at the minus side, that is 9 volts. Okay. So we have to look at how the magnetic flux changes in time. That will give us the EMF. We only care about the absolute value of the EMF because the sign will depend on how we hook up the voltmeter. And by the way, where do we hook up the voltmeter? If I want to measure its voltage, if I want to measure this voltage, the voltmeter will be hooked up at the ends of the moving rod. Okay. So let's focus on 2 time moments. And this will be the top view, okay, of the thing. At time t1, right, the rod is at position x1, and at time t2, the rod is at position x2, okay, and the rod has a length L. What is the area here? A1 is L times x1. What is the area here? A2 is L times x2. Yeah? We have the area of a rectangle. And what is the magnetic flux? The magnetic flux at the initial time is the magnetic field times A1, which is BLX1, and the magnetic flux, okay, in the second position is the magnetic field times the area BLX2. Okay, and the change in magnetic flux is magnetic flux 2 minus magnetic flux 1 BL x2 minus x1. And the absolute value of the EMF delta magnetic flux over delta T, this will be BL x2 minus x1 over T2 minus T1, okay, BL delta x over delta t, but delta x over delta t is the velocity. So this is BLV. This is the formula we wanted to derive. E equals BLV. Please notice that there is no more plus or minus sign here because that is meaningless unless you explain how you connect the voltmeter. In the booklet. E equals BVL. Same thing, yeah? I used an uppercase L because I don't want to confuse the lowercase l with the 1. But it's the same thing. Okay. Okay, now signs plus or minus are given because they are meaningless unless you explicitly show how you connect the voltmeter. Okay. What happens if you have n rods? You have n wires. Well, you just multiply by n. And you also have this formula in the booklet. Equals BVLN. So n is the number of wires. In a coil, the total magnetic flux total magnetic flux is NBA. Okay, total magnetic flux. So for each loop of wire, you have an area A. So area of one loop of wire is A. N is the number of loops. Okay. And this total magnetic flux is often called flux linkage. Flux linkage. That means the total magnetic flux in a coil that has several loops of wire. Now, this is how we understand the EMF using Faraday's law. We can also understand the apparition of this EMF using the magnetic force. That's very important because the induced EMF and the magnetic force are related to each other. Maybe we should write this down. The induced EMF and the magnetic force are related to each other. That is also apparent from the statement of Lenz's law. The induced, okay, Lenz's law. The induced voltage, the induced EMF, right? Generates an induced current that opposes the cause of the change in magnetic flux. Okay, if a change in magnetic field causes the change in magnetic flux, then the induced current will generate an induced magnetic field Okay, that is proportional to the negative of the change in magnetic field, yeah, to reduce the effect of this change. If a change in the area produces the change in magnetic flux, like we have in the example with the two rails, okay, then the induced current will produce a magnetic force that opposes the motion of the rod. Okay. So we can look at the magnetic flux and find the EMF according to Faraday's law, but we can also look at the magnetic force, okay? And this is what we'll do next. The magnetic force, we talked about this in the standard level chapter. Okay, what is the formula? Q V cross B. Okay, we have the vector product. Okay, also called cross product. Cross product. Okay, between two vectors. Q is the charge of the particle, electric charge. Of particle. V is velocity of particle. And B is the magnetic field. Okay. How do you calculate the cross product? Well, two methods to find the direction of vector product. Okay, I recommend you two methods. In the book, you will see a third method, something with a left hand or a right hand. I never liked this method because we already have a right hand method to show the direction of the magnetic field lines around a straight wire. And we can easily get confused with too many methods that rely on the left, on the right, or on the right hand. Okay, so these are the methods that work for me. The first method is to draw a reference frame X out of the page, Y to the right, and Z up. Okay, and then you simply know that X in a cross product with Y is equal to Z. Okay, another method is the so-called corkscrew rule. Which was the standard rule when I was a high school kid. Back then, high school kids could learn about how to open a bottle of wine. Today, this is more like a taboo subject. Okay. So the corkscrew rule tells you that you align the corkscrew handle okay, parallel to your first vector. Let it be v, the velocity in this case. Okay? And you rotate the corkscrew handle in such a way that now the handle points in the direction of the second vector in the vector product. In my case, the magnetic field. The direction in which the corkscrew moves, in this case, okay, in this case, the corkscrew goes into the cork. Okay, for this type of motion. Now, of course, if you rotate the handle the other way, the corkscrew gets out of the cork. Okay, and This direction in which the corkscrew moves tells you the direction of the vector product. So this is basically the direction of V cross B. Now, of course, you got to remember this is multiplied by the electric charge. If the electric charge is positive, that's the direction of the magnetic force. If the electric charge is negative, the magnetic force points the other way. Okay. If Q is greater than 0, okay, the magnetic force has the direction of V cross B. If the electric charge is negative, the magnetic force has the opposite direction. Okay. And now let's look at what happens in our rail. Yeah, we have a magnetic field that goes like this, and then we have the rod. We have the rod that moves with velocity v. Okay, that's a vector, the velocity. Okay. And inside the rod, what do we have? We have electrons. Okay, and these electrons are forced to move with the velocity of the rod, but they have an electric charge. So here they have a negative electric charge. So here we have a negative electric charge that moves with the velocity v. Okay, in a magnetic field, which means magnetic force acts on it. So the first thing we have to figure out is what is the direction of V cross B. Well, let me start with the X, Y, Z reference frame, yeah? This will be V, this will be B, okay? And this will be V cross B, okay? Which means I have to flip this, okay? I will rotate this 90 degrees around the x-axis, okay? It will turn into something like this, Z y, x. Okay, so the magnetic field is up like it should. Now I want the velocity to be to the right. So I rotate this around this axis 90 degrees. And what's gonna happen, I will end up with y this way, x this way, and z out of the page, yeah. Which shows me the direction of V cross B. So V cross B will be in this direction. But because the charge is negative, the magnetic force will be in the opposite direction. Okay? So while I'm moving the rod in the magnetic field, I have this magnetic force that pushes the electrons, okay, pushes the electrons towards one end of the rod. So I'm gonna have an accumulation of electrons here, yeah, and positive ions, okay, from where they left. So basically, this is like a battery that pushes electrons at the negative terminal, okay, taking them from the plus side, okay, and if I have a battery like this, it will produce a current, okay, from the plus to the minus side along the external circuit. So we can see that the induced current must flow this way. Okay, and I marked the EMF, the polarity of the EMF. So this is where the plus is, this is where the minus is. Okay, now what is the work done? What is the work done when a battery sends an electric circuit, sends an electric current in a circuit? Okay, it Okay, it's force times distance. Okay, now we need to look at okay, the magnetic force on a wire. Okay, we'll do that next. Now, can we relate this direction of the induced current to Lenz's law? Well, yes, because this induced current produces an induced magnetic field that goes the opposite way. Yeah, remember the right hand rule. Okay, the right hand rule. Yeah, if I have a wire with an electric current I grab the wire with my right hand okay, in such a way that my thumb shows the direction of the current and the other four fingers wrapped around the wire will show the direction of the magnetic field thus produced. Okay. And in this case, the magnetic field produced by the induced current will be pointing down. Okay, which means that the induced current will oppose the change in magnetic flux. Yeah, uh, this external magnetic field stays the same. The area increases, so the magnetic flux increases. How can I oppose this increase in magnetic flux? How can I decrease the magnetic flux? Only if I decrease the magnetic field, yeah? So the area goes up. It means that the magnetic flux goes up, yeah? Okay, induced EMF uh, lowers, yeah, the total B, and as a result, lowers the magnetic flux. So it opposes the change in magnetic flux. And that's what we see. The induced magnetic field lowers the total magnetic field. Okay. So that's how we understand the Lenz's law. Now let's look at the same problem from the point of view of the magnetic force acting on a wire. The magnetic force acting on a wire okay L I cross B, okay, where L is the length of wire, I is the electric current, and B is the magnetic field. Okay. So again, I draw the two rails and moving metal rod. Okay, and this time I'll say, okay, through this metal rod, I have a current I. And the system is in an external magnetic field B. Okay, now what is the direction of I cross B? Again, I draw my reference frame. This is the direction of the current, the first vector in the vector product. This is the direction of the magnetic field, the second vector in the vector product. And I points in the correct direction. This is my electric current. The magnetic field needs to go up. So what I'm going to do, I'm going to rotate the reference frame 90 degrees around the x-axis, yeah, which will give me something like this. This is I, this is, what am I doing here? This is B, this is a mistake. And this is I cross B. Okay, so there is a magnetic force in this direction, okay, which means that in order to make the wire move at constant velocity, that means zero acceleration, right? The total force must be zero. Okay, which means what? Which means I need an applied force to pull on the wire in the opposite direction. Okay, same magnitude. Okay. And after a while, the rod has moved a distance delta x. Yeah? After delta t, the rod has moved a distance delta x. Okay. What is the work done by the applied force? It is the applied force times the distance which is L I B delta x. Okay, and during this time, the induced EMF, energy supplied by the induced EMF, energy supplied by the induced EMF. What is the energy supplied by the induced EMF? It's the electric charge times the voltage. Yeah. Remember voltage, right? By definition, is a change in energy over electric charge. Okay, the electric charge. And these two expressions are equal to each other. And what else do we know? We know that the electric current is the electric charge that moves over the time. Okay. So I can write L times Q over delta T times B times delta X is equal to Q times E, and again, the induced EMF turns out to be the electric charge cancels. So I get L times B times delta X over delta T. Guess what? This is the velocity of the metal bar. So again, I derive the same formula, but this time based on energy considerations. Yeah, the energy that I put into the system to keep the rod in motion is equal to the energy that I get out of the system as electric energy. I also notice that the induced EMF produces an induced magnetic force that opposes the applied force. Yeah. This is also a statement of Lenz's law. Yeah. Please also notice that the induced current, okay, in the rod produces an extra magnetic force. So this is an additional magnetic force that opposes the applied force. That means it opposes the motion, right? It opposes the motion that changes the magnetic flux. Okay. And this concludes my discussion of the relationship between the magnetic force and the electromotive force, the induced voltage and Lenz's law. Okay, now let's look at some examples. Okay, on page 438, we have a worked example. Okay. So the graph shows the variation of magnetic flux with time through a coil of 500 turns. Calculate the magnitude of the EMF induced in the coil. How do we answer this question? The magnetic flux in 10 to the negative third Webers. The time in 10 to the negative 3 seconds. And I have a straight line that goes from 0, 0 all the way to the time here is 4 milliseconds. The magnetic flux here is 2.0 milli Webers. So quite easily, E is equal to delta phi over delta T, the change in magnetic flux, 2.0 minus 0 over the change in time, 4 minus 0, okay, Webers over second, that is 2 over 4, that is 0.5, and what is a Weber divided by a second? It is a volt, yeah? Okay. Super easy. Worked example number 2. A small cylindrical magnet and an aluminum cylinder, which is non-magnetic, of similar shape and mass, are dropped from rest down a vertical copper tube of length 1.5 meters. But this reminds me of the magic trick I did at the beginning of the school year. Do you remember the copper pipe with the two cylindrical metal pieces? One was a magnet, one was not. Show that the aluminum cylinder will take about 0.5 seconds to reach the bottom of the tube. The magnet takes 5 seconds to reach the bottom of the tube. Explain why the objects take different times to reach the bottom. Okay, well, with no magnetic force, you have a free fall. So no magnetic force, that means free fall. Okay, so you can use the equation. Yeah, x is equal to x0 plus v0t plus at squared over 2. Let's work with an x-axis going down. So the acceleration is positive 9.81 meters per square second. And they are dropped from rest. That means V0 is 0, yeah, from rest. And x0 is 0 by choice. So, and this x is the distance, 1.5 meter, the length of the tube, which means that the time is square root of 2x over a, square root of 2 times 1.5 meters over 9.81 meters per square second. Okay, the meters cancel. The square second moves on top. And because of the square root, we end up with the units of seconds. And if we do the calculation, okay, 2 times 1.5 is 3. 3 divided by 9.81 is 0.3058. And if I take the square root of this, I get 0.553 seconds, which is also the answer in the book. What's the answer for part B? Let's read it from the book. As the magnet falls, the copper tube experiences a changing magnetic flux, and as a result, an EMF is induced in the walls of the tube. This EMF results in a current in the tube. The current leads to another magnetic field that opposes the motion of the magnet by Lenz's law. There is an upward force on the magnet so that its acceleration is less than the value for free fall. Okay. Now, as we discussed when I did the magic trick, you can also look at what happens with the energy. Yeah, when the magnet falls through the copper tube, the induced EMF produces an induced current, which produces an induced electromagnetic field. Okay, this is basically a radio wave. And this induced radio wave spreads into space. Yeah, it moves from the place of the copper tube away in all the space around, in this way carrying electromagnetic energy. So the induced electromagnetic wave carries electromagnetic energy. And where does this energy come from? Well, guess what? It comes from the kinetic energy of the falling magnet. So the kinetic energy of the falling magnet drops down. The speed of the falling magnet drops down. Yeah. So smaller speed, that means a longer time to go from one end to the other end of the copper tube. Okay. What is your homework assignment? Read 11.1 and solve. Let's see what problems can I find for you at the end of the chapter. Solve problems. Come on, come on. Okay, problems 1, 2, 3, and 4 on page 471. Okay. Thank you for your attention and good luck with the homework assignment.